Now that we've mastered the basics of the dot product, let's talk about projections. To set this up, we want to draw a picture. Take a vector v and then another vector u, and let's just think of these both as position vectors, so they both start at the origin. Here's vector v, here's vector u. Imagine shining a flashlight perpendicularly to v, down like this. It's not vertically down, it's perpendicular to the vector v. And think of the shadow that the vector u would cast onto the vector v. It would look something like that. This shadow is called a projection. Let's go ahead and draw it in here. The shadow that the vector u casts onto the vector v, this is called a projection. It's a vector. This vector is called the vector projection of u onto v. This is the notation that we use for projections. We have the projection of u onto v. We can think of v sort of as the ground, so think of v in the base here. That's the vector that the shadow is being cast onto. U is the vector that casts the shadow. The vector projection of u onto v is a vector, and we can imagine it's the vector created by shining a light directly perpendicular from v and the shadow cast by the vector u onto v. This red vector here is called the vector projection of u onto v. And again, this is a vector. Let's simplify just a little bit. Instead of thinking of the entire vector, let's just think of the length of the vector. That would just be the magnitude. Let's think of how far it is from here to here. That's just the length of that shadow. And instead of thinking of a vector, we're just thinking of a magnitude here. This magnitude is called the scalar projection. The scalar projection has this notation, and it's just the length of the vector projection. Ultimately, we're most interested in the vector projection. This is going to be our focus. But we're going to develop the formula for this by using the scalar projection. So we want to talk about the scalar projection first. So this length, it's not a vector, it's just a magnitude. It's the magnitude of the vector projection, and it's called the component projection or the scalar projection. Let's develop the formula for this scalar projection, and in turn that will allow us to find the actual vector projection, which we're really more interested in. Let's visualize this as a right triangle here. So I'll go ahead and draw in this opposite leg. We have a right angle here. The angle between the two vectors we'll just call theta. And we know a relationship between this angle and the vectors using the dot product. This formula here gives us a relationship between the vectors, the dot product, and the angle between the vectors. So I'm going to write cosine of this angle in two different ways. On the one hand, I know that cosine of the angle is equal to u dot v divided by the magnitudes of the angles. That's the geometric formula using dot product. On the other hand, I want to think of this specific triangle that I've got here. I've got an angle with an adjacent leg here, an opposite leg, and a hypotenuse. The hypotenuse is the vector u, so the length of the hypotenuse is just the magnitude of u. Let's go ahead and write that in. This hypotenuse just has a length, which is the magnitude of u. I can write a relationship between the hypotenuse, the adjacent leg, and the angle using cosine. So on the other hand, cosine of theta is also equal to adjacent over hypotenuse. Let's write that down. Cosine of theta equals adjacent, which is that scalar projection, divided by hypotenuse, which is the magnitude of the vector u. I have two expressions for the cosine of theta. That means this, since that's cosine of theta, that must be equal to this. They're both cosine of theta. I'm going to set these equal to each other and solve for the value for the scalar projection. So this equals cosine of theta, but here's another equivalent form for cosine of theta. So I can write this as equal to the scalar projection divided by the magnitude of u. I want to solve for the scalar projection to find this formula. Well, I can multiply both sides by the magnitude of u, and notice I have that in the denominator on both sides, so that's just going to cancel on both sides. Here I have a formula for the scalar projection. It's just u dot v divided by the magnitude of v. Let's write that down. The scalar projection is equal to u dot v divided by the magnitude of v. That will give me the length of this shadow cast by the vector u onto the vector v. What I really want, though, is the vector projection. I want the actual shadow itself. I want this vector. I know how long it is, but I want the vector itself. So the way to get the vector itself will be first to find the unit vector in the direction of v. That'll give me a vector of length 1. Then I'll multiply the unit vector by the appropriate length, and that will scale up the vector to be exactly how long I want it to be. Here's how we get the vector projection. We're going to start with the scalar projection. This is a magnitude. And we're going to multiply that by the unit vector in the direction that we want. The unit vector in the direction of v is just the vector v divided by the magnitude of v. Again, it's really important to understand conceptually what this is doing. We're finding a unit vector in the direction that we want, but then we need to scale it by the appropriate amount so that it's exactly as long as this shadow. The length of the shadow is the scalar projection, so we multiply the unit vector by the scalar projection. That gives us exactly the vector projection that we're looking for. This equation reduces to a really beautiful and simple expression if we just do a step or two of simplification. So let's write in the formula that we just found for the scalar projection. That is u dot v over the magnitude of v, and we're multiplying now by v over the magnitude of v. In the numerator we have u dot v, that just stays the same, but in the denominator we have magnitude of v times magnitude of v. We can write that as v dot v. We found that the magnitude of a vector squared is equal to the dot product of the vector itself. So here's the final form that we'll write this equation in. The vector projection is equal to u dot v divided by v dot v all times v. U dot v, that's unchanged. Magnitude of v times itself, that's v dot v. And we're multiplying all of this by the vector v. Let's think through what are scalars and what are vectors here. U dot v, that's a scalar. V dot v, that's also a scalar. So I have a scalar here that I'm multiplying by the vector v. Does that make sense? Well, I'm finding a parallel vector to the vector v when I find this shadow. So I just need to know how much do I scale the vector v by to get exactly this shadow. This expression right here is precisely how much to scale the vector v to get exactly the vector that we want. So this is the formula for the vector projection, and we used the scalar projection to get there. One thing that helps me to keep track of this formula is to think of the subscript here. The subscript is v, and notice that that's in the denominator, so I think of subscript down low, denominator down low, and really there's only one u in this expression. I have u dot v, everything else is v's, u dot v over v dot v, and we're scaling up the vector v, so that's the way that I keep track of this formula here. So to summarize, conceptually, the vector projection is the shadow that the vector u casts on the vector v. Take a perpendicular light source to v, and the shadow cast by u is this vector projection. The scalar projection, which we use this comp notation, that is the length of the shadow. Let's practice using these formulas in some examples. Let's solve example 9. We want to find the vector projection of the vector 2, 1 onto 3, 0. So 3, 0, this is the vector that we've been calling v. 2, 1 is the vector we've been calling u. Using the projection formula, we're going to find 2, 1 dot 3, 0. In the denominator, we have 3, 0 dotted with itself. And we are multiplying all of this by the vector 3, 0. In the numerator, we get a dot product of 2 times 3 plus 1 times 0, so we just have 6. In the denominator, 3 times 3 plus 0 times 0, we just have 9. So 6 over 9 times the vector 3, 0. 6 over 9 is the same as 2/3. And if we multiply 2/3 by this vector using scalar multiplication, then the 3's will cancel and we just have the vector 2, 0. Let's try to visualize our answer to see if this makes sense. We'll go ahead and draw in these two-dimensional vectors. We have the vector 2, 1, which is this vector right here. That is the vector that is casting the shadow. It's casting a shadow onto the vector 3, 0. That's this vector here. So we're imagining taking a light source perpendicular to this vector and seeing what the shadow is cast by the vector 2, 1. Well, this light source would be perpendicular in this case to the x-axis. So if we imagine here what the shadow would look like, we can visualize that that does look like the vector 2, 0. So that is our vector projection. Let's take a look at example 10. We want to find the projection of 1, 0 onto 0, 1. Let's first solve this one geometrically and then confirm our answers using the projection formula. We'll graph in these vectors. The vector 1, 0 is just this vector right here. And the vector 0, 1, that's just this vector right here. So we're casting a shadow perpendicular to 0, 1. That means we're casting a shadow in this direction. And we want to know, what is the shadow cast by the vector 1, 0 onto the vector 0, 1? Well, if we imagine just a perfectly horizontal light source that's vertical to the vector we're projecting onto, then this vector that's supposed to cast a shadow, that's not going to cast any shadow at all. We're going to get the 0 vector as the answer here. There's no shadow cast because the vectors are perpendicular. Let's work through the steps. We take the dot product of the two vectors in the numerator, and then the dot product of the base vector, the subscript here, with itself. And we're scaling this subscript vector, 0, 1. So we multiply here by 0, 1. In the numerator, 1 times 0 is 0, plus 0 times 1, that's also 0, so the dot product in the numerator is just 0, which we expect because the vectors are perpendicular. In the denominator, we take the dot product of this vector with itself. 0 times 0 is 0, 1 times 1 is 1, so we get a 1 in the denominator, and then we're multiplying by the vectors 0, 1. But none of this really matters because everything's being multiplied by 0 here. The answer that we get would be 0 times this vector. So the answer is actually a vector. It's the 0 vector, 0, 0. We're scalar multiplying the vector 0, 1 times the scalar 0. So 0 times 0, 0, 0 times 1, 0. We get the 0 vector because this does not cast any shadow on that vector. Let's solve example 11. We have these two vectors, u and v. We want to find the projection of u onto v, and then find the length of the projection of v onto u. Our vector u is the vector 2, 5. The vector v is 9, 4. For part A, we want to find the vector projection of u onto v. So we set up the formula. u dot v divided by v dot v times the vector v. Let's work through these dot products fairly quickly. 2 times 9 is 18, plus 5 times 4 is 20. So in the numerator here we have 18 plus 20. In the denominator, we are dotting the vector v with itself. 9 times 9 is 81. And then 4 times 4 is 16. So 81 plus 16, that's the dot product of the vector v with itself. This is a scalar which we're multiplying by the vector 9, 4. And this simplifies to be 38 divided by 81 plus 16 is 97 times 9, 4. Notice again that the vector projection is just a scalar multiple of the vector that the shadow is being cast onto. So we're scaling back the vector v to be exactly the length of the shadow cast by the vector u. Let's visualize this in Desmos. Here's the vector u, which is 2, 5. Here's the vector v, 9, 4. We are finding the shadow that the vector u casts on the vector v. Try to visualize this. Imagine some light source that's perpendicularly above v, and it's casting a shadow from the vector u onto the vector v. Try to visualize what that would look like before we type it in. We found that it's 38 over 97 times v, so we're scaling back v by a factor of 38 over 97. If we do that, here is the vector projection. There it is. That is the shadow that the vector u casts on the vector v. We have a 90-degree angle from this point here to the end of vector u. We can visualize that like this. That's a 90-degree angle. We have a perfect projection of the vector u onto the vector v. The second half of example B is to find the scalar projection of v onto u. So we're switching the order here. We want to be aware of that. And the formula here is u dot v divided by the magnitude of the vector in the subscript here. So divided by the magnitude of u. Well, u dot v we already figured out, that's 38. And the magnitude of u is the square root of 2 squared plus 5 squared. So we have 38 divided by the square root of 29. That is the length of the shadow that the vector v casts onto the vector u. Let's wrap up our discussion of the dot product by looking at one physical application, which is an application to work. Here we have a force vector F, which moves an object a displacement of d. We've seen work problems before, and we've always assumed that the force acts parallel to the displacement. In this case, the force vector might not be acting parallel to the displacement. Let's draw a picture to wrap our minds around this. We've got some object here, and there's a force that's being acted on it. Let's represent the force something like this, and maybe the displacement looks something like this. So we have a displacement. We want to calculate how much work this non-parallel force performs in moving the object, the displacement of d given by this vector. Turns out that the work is simply the dot product of the force vector with the displacement vector, which is a really nice, concise, beautiful formula. And let's try to figure out why this formula is what it is. First of all, we want to think of how much force is actually acting on the object. Because the force is not parallel to the displacement, some of that force vector is being wasted. The only force that's actually moving the object is the component of the force that's parallel to the displacement. So we want to find how large that force is, what is the magnitude of that force, and then multiply the magnitude of that force times the displacement of the object. So we take the force that's actually parallel to the displacement. That would be the vector projection. We only care about the magnitude. So what we're really after here is the scalar projection, which we call comp of F onto D. That is the length or the magnitude of the force that's actually moving the object. The displacement is d, so to figure out work being done, we'll multiply the magnitude of the force times the length of the displacement, which is the magnitude of d. So the work being performed here is the amount of work that acts parallel to the displacement. That magnitude is this scalar projection. And we multiply the magnitude of the force times the distance that the object is displaced, which is simply the magnitude of the displacement vector. Using our formula for the scalar projection, this is equal to F dot d divided by the magnitude of d. And we're multiplying by the magnitude of d, so these magnitudes simply cancel out. So we're left with simply the force vector dotted with the displacement vector. This is a dot product between two vectors. That will give us the amount of work performed in total. This is a beautiful formula that allows us to calculate work performed by a force even if it's not acting parallel to the displacement of the object. Let's use this to solve the last example in this section. We have a force vector F described by 2, 1, 1, that's our force vector, and we want to know how much work was performed if that force moves an object from the point 035 to 3, 1, 11. Let's just assume here that the force vector is measured in newtons, and we'll assume that we're measuring distances here in meters. First thing to do is to find the displacement vector. The displacement vector is the vector between these 2 points. How do we find a vector with an initial point and a terminal point? We find the difference of the components. So the displacement vector d, the x component is 3 minus 0, 3. The y component is 1 minus 3, which is negative 2. And the z component is 11 minus 5, 6. The displacement vector is the difference between the terminal point and the initial point of movement. Here's the displacement vector. The force vector was given. It's 2, 1, 1. Now I can calculate work very simply by taking the force vector dotted with the displacement vector. So I take the x component of the force vector, 2, times the x component of the displacement, 3, and now I add 1 times negative 2, finally 1 times 6. So take the x components, multiply them together, 2 times 3, multiply the y components together, 1 times negative 2, multiply the z components, 1 times 6, add the results, and we have the dot product. Let's think about units here. Displacement is being measured in meters, so the 3, the negative 2, the 6, those are units of meters. The force is measured in newtons, so 2, 1, 1, those are components of the force, those are measured in newtons. In each one of these terms, we have newtons times meters. Newtons times meters is joules, the expected units for work. So to simplify, we have 6 minus 2 plus 6. The answer is 10 joules. That is how much work is performed when this force moves an object through that displacement vector. Notice that the force vector is not parallel to the displacement. So if we were just to find the magnitude of the force and multiply by the total distance traveled, we'd get too much work performed because the force doesn't all act parallel to the displacement. When we find the dot product, that's taking into account only the amount of force that's acting in the direction of the displacement.